Welcome to the Explainer. Today, we're going to break down the invisible glue that literally holds our world together. We're talking about covalent bonds. You know, from the water you drink to the air you're breathing right now, these tiny connections are the architects of pretty much everything.
So let's just jump right in with a really big question. Have you ever wondered why atoms even bother sticking together? I mean, why isn't the universe just a big random soup of loose atoms floating around? Why do we get all this amazing structure?
Well, the answer comes down to one fundamental driver in nature, the search for stability. The universe just favors lower energy states, and for atoms, teaming up is the best way to get there. By forming groups called molecules, they find a much more stable, low-energy existence.
And that's what a molecule is, really. It's just a neutral little group of atoms held together by these covalent bonds. Think of a single unit of water, H2O, or the oxygen you're breathing, O2. Each one is a tiny, complete building block of a much larger substance.
And to keep track of these, we use what's called a molecular formula. It's basically like a recipe or a parts list. H2O tells you, plain and simple, you need 2 hydrogen atoms and 1 oxygen atom to build 1 molecule of water.
Easy enough, right?
So how in the world do atoms actually form these connections? How do they get so stable? Well, it's all about finding an energetic sweet spot. It's a really delicate balancing act.
I want you to picture a ball rolling into a valley. When 2 atoms are far apart, their potential energy is basically zero. But as they get closer, they start attracting each other, and their energy drops, just like that ball rolling downhill. They settle at the very bottom of the valley. That's the bond. It's the point of minimum energy and maximum stability. But if you try to push them any closer, they start repelling each other, and that energy shoots right back up the other side of the valley.
And that sweet spot at the bottom of the valley gives us 2 really important measurements. First, you've got bond length. That's the exact distance between the atoms when they're at that lowest energy point. Then you have bond energy, which is how much energy it would take to rip that bond apart. It's really just a measure of how strong the connection is.
Okay, so what is the ultimate goal for an atom when it's forming a bond? Well, for most of them, it's to be like the cool kids of the periodic table, the super stable noble gases.
This leads us to something called the octet rule. You see, the noble gases, with the exception of helium, all have 8 electrons in their outermost shell, and this makes them incredibly stable and non-reactive. So other atoms try to achieve that same stable setup by sharing electrons through covalent bonds. They're all trying to get that magic number of 8. But, you know, like any good rule, there are a few key exceptions you have to know about. Hydrogen, for example, is perfectly happy with just 2 electrons. Boron often settles for 6, and then you have some of the bigger elements that can actually hold more than 8, which we call an expanded valence. Now, to help us see all this electron sharing, chemists came up with a fantastic tool. It's like an architectural blueprint for a molecule, and it helps us map everything out visually. These are called Lewis structures. They give us a simple 2D map that shows us exactly which atoms are connected and where all those important outer shell electrons are, both the ones being shared in the bonds and the ones that are just hanging out on their own. And drawing one is actually a pretty logical step-by-step process. First, you count up all the outer electrons that all the atoms bring to the party. Then, you arrange the atoms, usually putting the least electronegative one in the middle. Connect everything with single bonds, then distribute the rest of the electrons as little dot pairs around the outer atoms. And finally, the most important part, check to make sure every atom has its stable octet. We really hope this kind of clear breakdown is helpful for you. If it is, let us know by hitting that like button. But what happens when that simple blueprint of single bonds just isn't enough? What if you can't give every atom its stable octet that way? Well, that's when things get a little more complex. This is where atoms have to get, well, a little more creative with their sharing. If a single bond doesn't satisfy the octet rule for everybody involved, they can't just give up. There has to be another way. And there is. They can share 2 pairs of electrons, which forms a double bond, or even 3 pairs of electrons to form a super strong triple bond. A perfect example is the nitrogen molecule N2, which makes up most of the air we breathe. It's held together by an incredibly strong triple bond. Now, check this out. This slide shows a really clear and important pattern. As you go from a single carbon-carbon bond to a double, to a triple, 2 things happen. The bond length gets shorter, pulling the atoms closer together. And the bond energy, its strength, goes way up.
It's pretty intuitive. The more electrons you share, the stronger the connection.
Okay, but sometimes even throwing in multiple bonds doesn't tell the whole story. Sometimes a single Lewis structure, a single blueprint, just fails to capture what's really going on. This fascinating situation has a name: resonance.
This is a brilliant illustration of the concept. For ozone, O3, you can actually draw two equally valid Lewis structures. The thing is, the real molecule isn't flipping back and forth between them. It's actually a hybrid, like an average, of both structures at the same time. And we use that special double-headed arrow to show that.
All right, let's step back and bring this all together. Let's look at the big picture. What does all this sharing and bonding and rule following actually build?
The most important thing to take away from all this is that a few very simple fundamental principles, the drive for low energy, the octet rule, and a few different ways to share electrons, that's all it takes. That's the toolkit nature uses to build the incredible molecular complexity we see all around us.
And that's it. Right there. That's the engine of all of chemistry. This mutual attraction, this pull between the positive nuclei and the negative electrons is the fundamental force that turns individual, separate atoms into the very substances that make up our entire world.
It's a really powerful idea when you think about it. From just a handful of basic rules, you can get endless, mind-boggling complexity. It makes you wonder, what other systems work like that? We'd love to hear your thoughts on this in the comments below.
And that's it for this explainer on covalent bonding. Thanks for joining us. And hey, don't forget to subscribe and turn on those notifications so you don't miss our next deep dive into the forces that shape our universe.